welcome back everyone to the third and final leg of our journey for Global AM Summit. Now, previously we have touched on the subject of cellular agriculture and sustainable urban solutions and how AM has played a pivotal role in enabling this process. So for the next part, we will delve deeper, converging our focus on renewables and environment. And to open for this session, I'm pleased to welcome a familiar face and an old friend of NAMIC, Vice President of Content Strategy and New Product Development at Rapid News Group, Daniel O'Connor. Daniel, please.
Thanks very much, ladies and gentlemen, for joining us for this final session here at Global Additive Manufacturing Summit 2023. My name, as it says up there, is Daniel O'Connor. I am the Vice President of Content Strategy at Rapid News Group. But what that means is that previously I was the editor of TZT magazine, our flagship 3D printing magazine. When NAMIC approached me and asked if I could write some opening remarks for a session on sustainability, my mind was immediately cast back to June in this year when I moderated 2 sessions in a medtech show and a 3D printing show on the same day. What was interesting about those 2 talks was how different they were. The first was Boston Scientific, and they were talking about how the NHS, the National Health Service in the UK, has mandated to them that they must be net zero by 2030. The NHS didn't say, here's the roadmap for you to take. They simply threw Boston Scientific the hot potato and said, you deal with it. In turn, Boston Scientific have had to go to their supply chain and do the same thing, but they're also taking a little bit more of a holistic approach. One of the interesting things they're doing, for instance, is they are putting a carbon budget on employee travel, something that I would have blown out of the water in the last 2 weeks, bearing in mind I was in China a week ago, back to the UK, here to Singapore, home tonight. They asked the NHS if they could have any pushback on some of the regulation that they felt was holding them back. One of those regulations is that in the UK, every single medical device must be supplied with a piece of paper. They asked the NHS if, even for the most simple devices, they could switch to QR codes. The answer was no. We are afraid if our digital infrastructure goes down, then we won't be able to treat patients. The second speech I moderated was by Dr. Phil Reeves, who is very, very good at cutting through some of the, how do I put this, marketing material that some of the additive manufacturing companies put out there. He was particularly focused on some of the greenwashing. And those 2 talks, what with the paper problems that Boston Scientific faced and the greenwashing that Dr. Phil's talked about, reminded me of when I started in this industry 10 years ago, a now defunct OEM, who I feel like I can criticize now without losing my job because they don't exist anymore, they claimed to be the most eco-friendly 3D printer. Their claim was solely based on the fact that they were using paper over plastic. There was no study done into how harmful deforestation is to the planet. There was no study done into the harmful glues or the dyes that they used, let alone the material wastage that they used. Fortunately, we've moved away from that kind of greenwashing exercises, and we're starting to see some really interesting applications of additive manufacturing for renewable energy and for sustainability. And that's why I'm really looking forward to the rest of this session that we've got on for you today and for our panel session. Please do jot down any questions that you have for our next speakers, because we will be able to have some time to ask the questions during the panel session. Anyway, thank you very much, and I'm going to hand back to our MC.
Thank you, Daniel. Thank you. So Daniel will also be moderating our panel later, so feel free to ask questions like he said. All right, as we have looked at a lot at the utility of AM in concrete in the previous session, we'd like to explore another type of material for this one. So amongst raw materials, metal is one of the most versatile and commonly used in a wide range of industries, aerospace, automotive, and electronics, just to name a few. So how then can we leverage metal additive manufacturing for a sustainable industry? So to speak to us all about that, please join me in welcoming Pauline LeBon, General Manager at Cetim-Metco.
Good afternoon, everyone. Thank you so much, NAMIC, for the invitation and the possibility to speak to this wonderful audience today. So yeah, we had, I have a button I think I can use, right? Yeah. So yeah, there is a big challenges today to address regarding sustainability and how we can leverage metal additive manufacturing for a sustainable industry. This is something we'll have to take in consideration anyway today. So I will give you a bit of the background to explain why I'm here today, and then define what we think is sustainability for the AM industry, and then go through some cases to explain that today we have already some answers, but the work and the path is still to be built in the next years. So CETIM is a technical center for the mechanical industry. So we are basically the link between the research and the industry. So we'll help in leveraging on the readiness level of the technologies, all the new technologies up to the industry to make sure that they can handle the next challenges of our ages. So related to mechanical industry, you will need to tackle all these topics on material, product, processes, on the way the system can perform, actually, and then also how you make sure everything is sustainable, safe. Today we are located worldwide, and I'm speaking to you today because I have the chance to manage the Singapore subsidiary of CETIM Group. We work on extending the life cycle of the industry in APAC, running failure analysis, asset integrity management, and sustainable industry study for all the different industry you could see on the screen today. Related to additive manufacturing, we have a strong base, so it's important to let you know that we've been studying a lot of different metal additive processes from the entire value chain, from the raw material up to the performance of the parts. So what are the promises and the challenge of metal additive manufacturing today? As you all know, I mean, industries will have to tackle a lot of requirements, regulations, and most of all, make sure they sustain their activity addressing those environmental challenges. So we can talk about net zero, we can talk about a lot of different aspects of the industry, but there's also a lot of different subjects that you need to tackle. Obviously, you can have a very good technology, very good in carbon emission, getting them low, but economically not sustainable, or that could be dangerous for the society or not well accepted by the public opinion. So this is where we think that a sustainable development of a technology, especially metal additive manufacturing, and we'll see why, need to tackle the three axes of the sustainable development to make sure the industry will actually acquire. First of all, the first one will be the economic aspect. It has to be competitive. Second one, the environmental, obviously. It has to be cost-effective and environmental friendly. And at the end, social. We need to address also this aspect. And we'll see through the next example that we can answer some of those topics, but until now, on the metal additive manufacturing, it's not a complete answer that we have today addressed by the industry. So regarding economic sustainability, everyone has seen this, I guess, the GE fuel nozzle that is brilliantly designed to reduce the number of parts, to have a lightweight part. So it's economically sustainable, it's environmental sustainable as well. And we'll see later, is the LPBF today, from our perspective, environmental competitive? But let's go back on the economic part. So with metal AM and AM in general, you can have also the process itself and the supply chain that will be helping in the reducing the time to market. You can be more cost effective also on the product you will launch on the market. This is also another example you've seen on the screen from Vallourec and Total Energy on demand. When you need to solve an offshore problem quite quickly, you can get a quick answer and to make this solution more economic and sustainable as well. Then we heard a lot about, it's metal AM, the production, the printing can be slow sometimes. It's not really efficient. But with some new technologies, we can also think about mass production today to address, let's say, large markets like automotive industry. So if we go for cost-effective mass production, we think about metal binder jetting. So as a 3D printing process, you can relocalize your production and get more reliability, predictability in your supply chain, and sustainability. So I will give you this example that will address the three different ones. So this is the industrialization of a locking system. So it has been redesigned, so relatively to the economical aspect in the middle, you will have a cost efficient, you produce more, you have a better performance, and then in environmental aspect, you can also address the faster time to market, reduce the different stages of your supply chain, and socially, job creation in the company, and also development of new knowledge that will help in accepting also those new technologies. Relating to environmental, so this is a key aspect. If you take this graph, sorry, it's not really easy to read, but on the first part, you will get the conventional part, energy demand. And then on the bottom part, the AM part, energy demand. If we subtract the one from the other, we would like to have a positive impact, obviously. So today, we all agree that to get the environmental impact of additive manufacturing, you need to take the global life cycle itself. Because yes, the usage of metal additive part, we'll see, can be today, it's already proven. Okay, you can have a lot of freedom in design. You can have reduction of parts, reduction of assembly. So in the use of the products, reduction of energy of usage. Reduction, we said about the supply chain, also environmental impact is very good. Economical impact, also, if you reduce everything, okay, this is proven already. Thanks to a lot of different, all the freedom that the design is used for metal AM. But what about the process? If you go back a step before, we did a study with the CNES, the National Center for Space Studies in France, using 5 indicators, the key indicators you will see in the bottom of the slide, using 4 different materials and the use of 283 builds between 2013 up to 2022. So a large database has been used. And what we can see is that related to equal mass, stainless steel will have less impact than titanium and Inconel on those 5 indicators. And that for all material related, you will get actually a more impact on the environment. The most impactful aspect will be the neutral gas and also the powder that you will use. This was for more sampling parts, for kilograms. Then if you take a part itself, the comparison between a conventional manufacturing process and metal AM, you will see that using only the material and the process of printing, you can actually not conclude. Meaning in a way that we need to we cannot generalize that AM will be more powerful and will have less environmental impact today. And that will vary also on the material you use and the usage also of the part later on. Last but not least, the social sustainability. A lot of different points to tackle here. Safety and health. We've seen a lot of improvement in health services thanks to AM, metal AM mainly, for shortened medical acts and also faster user recovery. And at the same time, we've seen also mainly on powder processes that some risk need to be also tackled on this for the acceptability. We've seen industries that have been chosen the material not because they needed this material, but because it was accepted by their QSE department. So this is something also that has to be a driver and be taken into consideration to the development of AM. Then the data privacy and security, how we can protect this data, the IP, how can I protect my design, especially if it's brand new. And then regulation and standards. I've participated to a few workshops this week, and this is a key. This is a key aspect also, the social acceptance and the industrial acceptance through standards and regulations that will help in giving confidence to the industry. So a few examples that now we've been able to have case studies, regulations exist, standards exist, and they are already certified, and some patients are using already orthopedics implants. We also have chirurgy accessories that will help in performing surgeon act. And then we'll give you an example of what we are working on also at CETIM. We are thinking also that the development of the metal AM, which has a lot of archaic steps in the process, will be also helped by the automation of all the lines. This is why we worked on a fully integrated line, especially on metal binder jetting, that will help in faster the mass production of those parts that we've seen earlier, may have a very huge impact on the economic and environmental impacts. So globally, our perspectives. We need always to tackle those three aspects to make sure that we will not redo the same mistake that we did for other processes. So always thinking about the environmental, economical, and social impacts of what we develop, and that we will need to collaborate together because we have a lot of lock to unlock actually on those technologies. Metal AM will help to address critical aspects and critical parts in the next future. So this is something we really need to go through. This is why we are not working alone. We work with a full branch of partners in the US, in Europe, and here also in Singapore. So thank you for listening to me, and I will be pleased to answer your questions during the panel discussion. Thank you very much.
Thank you, Pauline. So if you do have any questions, please feel free to post it to Pauline either now or later at the panel discussion. So if no questions from the crowd, I think they're saving it for later to attack you all at once. No, just thank you so much. Thank you. All right, the economical, environmental, and social impact are some of the most universal benefits that we can reap with the use of AM. But beyond that, as Minister has mentioned this morning, it also cultivates innovation. Just look at what the amazing architects did with the buildings in the previous sessions. The only limits are our imagination. So for our second topic of discussion, we shall take a look at a different application of AM in thermal management. Now, for the majority of us, I think thermal regulation of electronic and data centers is probably not something that comes to our mind too frequently. But with a total of 7% of the total electricity demand of Singapore, it is indisputable that a greener solution to manage the usage is necessary. So how then can AM enable that? To speak to us more about it, we have founder and CEO of Coolest DC, Professor Lee Po Seng, up on stage. Please.
Very good afternoon to all. So today I'll be sharing our work on additive manufacturing enabled leak-proof direct-to-chip liquid cooling for data centers. So besides being the founder of Coolest DC, I'm a faculty member at the Department of Mechanical Engineering at NUS. So the agenda for today's presentations are shown in the next slides. I will start by providing an introduction to direct-to-chip liquid cooling, DCLC. Then I will describe the challenges in implementing direct-to-chip liquid cooling in data centers. Then I will So go through some of the solutions for overcoming the challenges in additive manufacturing. Then I will end the presentation with some conclusions. And if you have any questions, I'll be most happy to address them. So the the challenge that the MC mentioned just now is actually very much ties to the fact that due to COVID, due to digitization, so there's actually increase in the consumptions of digital services, right? So in particular, if you look at some of the latest announcements by the chip manufacturers, right? So they have actually mentioned that the thermal design power, be it for the GPU or the CPU chips, are actually going up to the level of 400, 500, 700 watts, and in time to come, it will actually reach 1,000 watts. So associated with these high power chips, so there's a need to sort of manage temperature, right? So that the servers, the IT equipment can be operated reliably and efficiently, right? And the conventional cooling techniques is actually using the liquid air cooling, right? Which most people are very familiar with, right? Which we also use for building cooling applications. But with such a high level of power, air cooling is actually approaching its physical limit. So that's why there's actually a interest to transition to more efficient liquid cooling. But to support this transition, we need to actually address some of the issues or concerns, right, related to the use of liquid cooling. So let me quickly touch on that. So just now, I think the MC mentions, and it is right now, the data center is really consuming a lot of energy, right? In Singapore here, it's actually taking up about 7% of our electricity demand. And if you look at on the global level, it's already consuming between 1 to 1.5% of the global electricity use. And related to that is actually the very significant carbon footprint. So it's estimated to be about 1% of the energy-related GHG or the greenhouse gas emissions, right? So that's why it's actually imperative for data center industry to actually look into more efficient way of reducing the energy, the consumption, and the associated carbon footprint. This next slide actually shows the current cooling solutions and the limitations. So when I say limitations, it's actually pegged to rack density, right? Which is actually how much power your IT equipment is actually dissipating, right? So if you look at on the left end of the chart, right? So when rack densities are low, right, you can still safely go back to the tried and tested air cooling. But as rack density increases, right, then you need to then look at more efficient forms of cooling. And this includes direct-to-chip liquid cooling, immersion cooling, spray cooling, things like that. And we are already seeing the transition, right? Because the rack densities is now between the average rack density is actually about 12 to 15 kilowatts. And as more and more companies goes into generative AI or even the general AI applications, right? So the back-end IT infrastructure would then certainly experience an increase in the rack or power density. So along with that, certainly we need to look at more efficient forms of cooling, right? So next, I'll do a very quick introduction pertaining to the liquid cooling. So liquid cooling is actually not new, right? In fact, it has been around for a number of decades, in fact, as early as the 1960s, right? But why didn't we actually transition to liquid cooling, right? So if you are into the IT space, so you know that associated with the multi-core technology, so the heat flux have actually flattened for a number of years. But if you look at what's happening over the last 5 years or so, so the power density has actually started increasing again. And this is actually very much still obeying the Moore's law, which states that the number of electronics components within a certain footprint will double every 18 months, right? And then obviously associated with this doubling of electronic components, it also leads to an increase in the heat density that needs to be effectively dissipated, right? So that's why now there's actually interest, as mentioned, to look into high efficiency liquid cooling. Why the interest to go into liquid cooling? So if you look at air versus, for example, water, right, which is one of forms of liquid cooling is actually hundreds, if not thousands of times more efficient, right, in terms of managing heat, right, because of the thermal properties or thermal physical properties of liquid being a lot more superior compared to air cooling. The other the advantage is actually pushing liquid is actually a lot more energy efficient than pushing air. So that's why operating liquid cooling system will then also translates to a very substantial energy savings, right? Then, as I've shared just now, associated with the increase in the rack density, so certainly the use of liquid cooling can actually allow you to actually support these more power-intensive workloads. One concern when it comes to liquid cooling is actually how do you then actually scale in a very cost-effective fashion, right? Because while there have been a lot of talks related to generative AI, right, because of the ChatGPT, whatnot, right? But in terms of the actual take-up, it wouldn't actually happens overnight, right? Meaning the transition for lower density rack to higher density rack, it wouldn't actually happens overnight. It will actually take time, right? So it's important to come up with a liquid cooling solution that is actually modular, yet easily scalable and cost-effective in terms of scaling. So that's one aspect. So my startup company, Schoolers DC, we have been working with data centers, industry, the players, including operators, consultants, to actually come up with different configuration that would actually support either the green retrofit of brownfield data centers or for the new build data centers, right? So these are some of the configurations that we have actually test-bedded in a local data center operator sites, right? And we have actually shown that the solutions, all the three solutions are very effective, right, in terms of sort of managing the heat as well as reduction of the overall energy consumptions. But one the other issues that is sort of preventing liquid cooling from sort of being deployed widely is the leakage concern, right? Because as you mentioned, for air cooling, there's less concern of leakage, right? So meaning if there's some air leaking out from the rack, whatever, it's actually not going to pose any serious issue. But if you were to plump liquid into your IT cabinets, into your IT racks, into the server, if let's suppose there's actually a leakage, then that can potentially damage your costly IT equipment. So that's why the ability to actually address the leakage risk is actually the paramount in the sort of helping to sort of push for the wide adoptions of liquid cooling. So what we have done is actually by working closely with EOS, we've actually realized what we call a unibody leakless cold plate, right? So a traditional cold plate actually comes in different parts, right? So you actually have a base plate that comes with the fin structure or the microchannels, which the liquid will actually flow through. Then you have a top cover, because again, going back to what I mentioned, you need to contain the liquid, right? You don't want the liquid to be obviously the leaking out of your heatsink or cold plate. So that's why there's actually a separate top cover. Then you have the connectors, right? So whenever you have different parts coming together, so even if you were to go through a joining process, right? So the joint quality wouldn't be 100%, or even if it's good for a start, over time the joint quality can degrade. So that's why this is actually one of the potential risks associated with the use of conventionally machined cold plates. So what we've done, right, is actually come up with a unibody design whereby the base plate, the top cover, as well as the connectors are all in one integrated piece. Okay, let me go to the next slide, which is actually shown in this illustration. Right? So what I mentioned just now is actually the conventional design on the left-hand side, right, which comes in different parts, right? As mentioned, the top cover, then some sort of joining process. So if you were to, obviously there are different types of joining process. It can be through the use of O-ring gasket, or it can be through the use of, for example, some sort of a brazing process, right? Then you have the base plate that contains the fin structure, the microchannel. So there's a conventional design which is prone to the leakage, right? Then on the right-hand side is actually what we have actually realized through the use of additive manufacturing, right? So what the process in itself is what I call a thermal AM co-design, right? traditionally, when the thermal engineers design heat sink, cold plate, heat exchanger, is actually you come out with design first, right? Then you talk to the manufacturing partners to see how to realize it, right? And sometimes because of certain manufacturing constraint, you go back to the design board, right? You make some changes, then again, it becomes an iterative process. But this process is actually quite time consuming, and there's no assurance that the eventual realized heat sink, cold plates, and heat exchanger can actually meet certain performance requirements. But for additive manufacturing, given that it offers a lot of design freedom, so what we've done with EOS is actually to work with them at a very early stage, even when we're actually conceiving the idea, right? So that we actually fast track the design to the realization, right? So this is actually one of the latest design that we have realized, as mentioned. So we are able to sort of have the base plate, the fin structure, the top cover, as well as connectors as one integrated piece. And in doing so, we actually eliminated all mating surfaces, right? So there's no possibility of leakage, yeah. And we've actually test-bedded these cold plates, right, by mounting them or integrating them into the servers, right, and tested them in production data centers. Let me show you the next slide, so which is what I mentioned. So we actually integrated the cold plates in an actual 1U server. So these are actually very low profile servers because liquid cooling is actually very efficient. So that's why the profile can be a lot lower compared to a conventional air-cooled heatsink, right? So that actually allows us to make the server very extremely compact, right? So this particular 1U server is actually dissipating about 1.1 kilowatts, right? So within a standard 42U racks, we are able to pack up to, if you want, 42 1U servers. So meaning that one rack can give 42 kilowatts. It's actually very intense. But you look at the details, each of the servers actually comprises of 4 GPUs and 1 CPU. So basically, we remove all the air-cooled heatsink, then we actually integrate the AM unibody leakless cold plates, right? Thereby actually allowing us to manage the temperature very efficiently, which I'm going to show next slides, yeah, which is quite interesting. So as mentioned, we collected the data in a production environment, so it's actually not a regular research lab, right? But to show the readiness of technology, I think there's a need for us to do the real-world testing. So with support of the Temasek Foundation, we actually did a 15-month test bedding in one of the world's largest co-location data center. And these are actually the data that we obtained. If you look at the left-hand side, it actually shows a comparison of your chip temperature, right? Both for the CPU and GPU. The red bars denotes the air-cooled chip temperature, right? And the blue bars denotes the liquid-cooled chip temperature. So you notice that the temperature actually dropped very substantially, sometimes as high as 40 or even 50 degrees Celsius. But you ask me, right, so what's the big deal about actually having such a big reduction in temperature? So that's actually shown on the right-hand side, right? The top right-hand corner actually shows the server power consumption, right? So we're able to slash the server power consumption by as much as 30%. So that's very substantial. As mentioned, that 1U server regularly will actually consume 1.1 kilowatt, right? But once I switch from air-cooled to liquid-cooled cold plates, right, I'm able to drop it from 1.1 to about 750, right? So it's actually easily a 300 plus watts reduction in terms of the server power. The other advantage is actually once the temperature is actually a lot lower, we are able to enhance the IT performance, which we measure in terms of clock speed. This shows a 40% improvement in the IT performance. So meaning your servers is not only very energy efficient, it's actually very high in performance. Yeah. So that's actually the advantage of high performance liquid cooling and obviously addressing the leakage concern. So I think I'm a bit out of time, but I'll just end with this PUE table, right? So comparing to the conventional technology, which is achieving a PUE of 1.41, we are able to achieve a PUE of 1.08. So that actually represents more than a 50% reduction in terms of the cooling energy system. But over and above, you remember what I mentioned, right? So we are able to slash your IT power consumption by another 30%. So if these two are added together, you're actually looking at a overall energy consumption savings of between 30 to 50%, which is obviously going to be very substantial and certainly helps to reduce the associated carbon emission. So with that, I will end the presentation. Thank you.
Thank you, Prof. Lee, for the presentation. Now, with the digital services industry growing exponentially, managing the energy usage for these industries is crucial. With the stack-on-stack technological innovations like what Prof. Lee has presented, we're now in an era where even sustainability can be efficient. So thank you for the sharing. And for our last presentation of today, of the Renewables and Environment session, I think it won't be considered complete without touching on renewable energy. Now, with a lot of buzz for carbon-free energy and the emergence of innovation at unprecedented speed, how can AM be a solution to these relatively newer and emerging technologies? So to share with us a little on that, please join me in welcoming from TAE Technologies, Project Engineer Vincent Pilar.
Okay. Good afternoon. Before starting, I'd like to thank NAMIC for the organization of this week and invitation to the Global Summit today. Also A-Star and EDB for the very interesting exchanges we had in this beautiful Singapore. So today I'm going to talk about TAE Technologies, which is a private company doing research in fusion energy and has developed also spin-off technologies from this expertise, and how we have implemented additive manufacturing in this domain. First of all, as executive summary, I'd like to emphasize that fusion energy will be one of the major actors in the future within the renewable energy mix. And TAE has a unique approach in this domain that I will explain a little bit after to provide a sustainable and clean and safe energy to the grid. Besides that, the other applications have more commercial exit right now and can cover a lot of electrical solutions for the future, and as well in life sciences. And sorry. Also, to understand that these cutting-edge technologies such as AI and additive manufacturing can be really enabling these advanced technology such as fusion energy or new system of energy. So I will start first of having a quick snapshot on the energy and the renewables, then explain you what is fusion energy, because I mentioned that several times, but not everybody knows about it. And then I'll move to what we are doing at TAE. So by the mid of the century, the demand on energy will almost double or more with the access to the needs for many people, the increase of population. So you see on the right projection only for the United States that the renewables will be almost half of the production of the energy in the future. And within that, we truly believe that fusion energy will be one of the main actor. So fusion energy, say that several times. Not everybody knows what it is, but everybody has seen a fusion reactor, and most see it every day. What it is the energy of the stars. That's how the sun powers the energy that created life on Earth, and the whole energy in the universe comes from fusion. So what it is when you have two light elements under certain condition, when they are close enough with a very high energy together, they are able to overcome the natural repulsion forces and fuse together. And when they fuse, they create another element, which is lighter. And the balance of this reaction is heat and light. So in the sun, this operates because of the huge gravitational forces that you have. And these all boiling gas that we call a plasma is the fourth state of the matter. It's an ionized gas. Happen in the universe, so all the stars, as I said. So the goal of fusion energy is try to recreate these reaction on Earth with obviously other approaches to ensure the ignition and the confinement of these plasma, because we cannot deal with gravitational forces. So TAE Technologies and what we do about fusion power. So I said you fuse two light elements. The first, the easiest reaction to do is with two isotopes of hydrogen, which are deuterium and tritium. When they fuse, they create helium and energy plus very high energy neutrons. So that's the easiest fusion reaction to achieve on Earth. And you may have heard that already, like big projects such as the JET in the UK or ITER built in France, which is an international project. Also the stellar radars, like the one built in Germany, the W7X. Or recently, you may have heard in the news, the NIF in the United States that has been able to fuse a little pebble of deuterium tritium with lots of lasers arriving on this small target, and this is called inertial fusion. The price to pay with this easier reaction is, as I said, the very high energy neutrons, which means that your machine has to be pretty complex because you will activate your machine. So it will become a nuclear facility, and you will also create radioactive waste, which the tritium is already a radioactive element, but because of the neutrons, all your machine will be activated, so you won't be able to do any maintenance on it. Everything has to be remote handled, so it's a very big and complex machine that needs also a framework, a regulatory framework to manage these waste. So another approach is to fuse PB11. So it's a proton-boron fusion. Boron can be found anywhere on the planet. It's very easy. When they fuse, they create 3 alpha particles, which is, by the way, the original name of the company, 3 alpha energy that gave TAE, and energy as well. So same in the form of heat and light. And the goal is to recuperate this energy to create electricity, obviously. So the technology that TAE is following is called, the type of a fusion platform is called the field reverse configuration, or FRC. And this is driven by very high energy beams, as you can see on the animation here, which are particle accelerators of hydrogen that fuels the beam, the plasma in the center of the vessel. So you see how it starts. You first shoot the 2 plasma at supersonic speed. They collide in the middle of the vacuum chamber. And then you shoot the neutral beams all around. So when the neutral beams collide with the plasma, they transmit the energy and give a spin to the plasma. So giving a spin, this increases the magnetic field of the plasma, increase the confinement, so it becomes its own magnet. So that's why you have a way much more simpler design. As you can see, it's a cylindrical vacuum vessel compared to the tokamak or stellar radar. And these also reaction, as I said, is considered as anuclear. There's no production of neutrons, so it's way easier to maintain and to build. So you see here on the animation, this is actual plasma that has been shot in our current facility. So TAE Technology is a company that's been created in 1998 from the University of California, Irvine. As you can see, there's been an evolution since that time on different fusion platforms, up to the current one called C2W, or renamed Norman, to pay tribute to the founder of TAE Technology, Professor Norman Rostocker, who was an eminent professor in plasma physics at UCI. The company is around 400 people now all over the globe, but on the fusion side, it's around 200 persons that have built these different machines, as you can see, at a very fast pace. And we are now building the new generation of the machine, Copernicus, that will achieve new records in terms of temperatures. So talking about temperatures, as I said, in the sun, these temperatures, to be able to fuse the element, are around 15 million degrees C. In a tokamak or a stellar radar, you have to achieve 150 million degrees C. Because proton and boron are heavier element, you need to add more energy. And so the plasma temperature you have to reach are 1 billion degrees C. So it looks a lot like this. Obviously, no material on Earth is able to sustain this temperature, and that's why the plasma is contained with the magnetic fields. So the current machine, Norman, has been designed for 50 million degrees C and has achieved recently a plasma of 75 million degrees C. Copernicus will achieve 150 million degrees C, so that's the DT equivalent fusion conditions, although we are still pursuing PB11 fusion, so there won't be DT used here. And this will be the final step before the commercial power plant called Da Vinci, that this will be the last step before having a commercial power plant that can provide safe energy to the grid, safe electricity and abundant based on fusion energy. So, as I said, it's a very high temperature, but that's not all. Everything operates in very high vacuum. We also have high voltage, high electrical fields, heat fluxes coming from the plasma and from the neutral beams, as I explained. So these particle accelerators you have on the side that gives transmit energy to the plasma and give it spin to it. So that means that you have a lot of complex components in a fusion power plant. It's not an easy thing to manufacture. And here you have to deal with very performant materials and high performance fluid dynamics to be able to cool down your components. Plus, because it's a complex machine, you want to have reliable components. So how to achieve that? Well, you have to minimize the number of joints, simplify your design, have a clever integration of all the components to keep your system compact, easy to maintain, easy to assemble, and so with the highest level of reliability. So that's where, 2 years ago, we started to do some implementation of additive manufacturing in our design. I give you here an example of a beam dump. So it's basically a component that receives a high heat flux beam, and so you have to cool down this system. So on the left, that's how conventionally it's done in every system in the world. Any kind of fusion reactor, you have these kind of swirl tubes with plates that are welded, 90-degree angles drillings, and pipes that are welded. So weld means quality control, potential failure point, so leak, and when you have a water leak in a vacuum chamber, that's a catastrophe. You have to shut down your machine and repair and start again. So we decided to move to a monolithic build with the same footprint, with another material, copper, chromium, zirconium in this case, and we saw that by integrating clever gyrates and just in and out connections, we're able to divide the weight by 2 with the same performances and even better. So this is just a school case for now. It's not a functional component, but can be the base for a design. And it was a way also to train the team, because that's another approach when you design with additive manufacturing. It's not at all the same concept and education where you have a block of material that you have to machine and then assemble. So we have to integrate that and take advantage of what additive manufacturing can provide. Another example here, the part here, this is part of the neutral beam systems called plasma generators, but just to give you an idea, this was a stainless steel base with a copper, chromium, zirconium plate that has to be brazed. It came back with a very high price tag and very long lead time from the manufacturers in the United States, and so we decided to redesign it in only one piece. Made only with a copper alloy called GrCop42, which is a material from NASA. It's a copper chromium niobium alloy that has very good mechanical and thermal properties. And we have been able to remove the brazing, so reduce the price by 3 and the lead time by 2. So that was a big progress. And actually, this part has been assembled, tested, and now is the standard in our prototypes. And that's how we will build the plasma generators for Copernicus. And I'm very confident that's the way we will build it for the future power plants. So it's another example where it's not because it's more performant, it's just because it's easier to manufacture. We don't have to do deep drillings that then you have to weld, to put a cap and weld. You have a better flux because you have nice curve in your channels, so you have less pressure drops. So it's a big advantage here. Another example are the grades still with the neutral beams. So as I said, they are sort of particle accelerators. So you have grids at different potentials where you accelerate your particles of hydrogen to be injected in the plasma, as you have seen in the animation. So here again, we had to, because we are going to a bigger machine with a higher energy, the grids that previously were cooled only by inertial cooling are now requesting to have internal cooling, so active cooling. So how to integrate a tiny cooling channel in a flat component? Well, you have some solutions in conventional manufacturing, but are pretty expensive and slow to do, such as electrode deposition, and with some risks, because it's still a sort of joint that you create, so you can have leaks, potential leaks. And so what we decided is to move to additive manufacturing design with integrated channel here. Another example, big box. So this one is the biggest component we will print pretty soon. This is, we changed the material and we integrated all the grooves and cooling channels we wanted instead of having plates to weld. So once again, we simplified the manufacturing and reduced the cost. Then think about the future. There will be the back end also. It's not only a fusion power plant, but you have to create electricity. So to all the turbines and everything. This work has been done by EOS. This is not a TAE work. You can see that additive manufacturing can also play a role here in the whole chain of creating the energy and then transferring that. So we're looking to the future as well on new materials and including graded materials for the future platforms. As you can see with the refractories and ceramics to cover the different needs in this very complex machine. So with the experience on the fusion, TAE has created a sister company called TAE Life Sciences that has developed a boron neutron capture therapy. How does it work? It's based on the boron drug that attach to the cancer cell naturally. And when it's bombarded by the very calibrated neutron beam, the neutrons destroy only the boron because they have a natural affinity together. And so they destroy only the cancer cells without destroying the healthy cells. So it's a better experience for the patient. And also without destroying the whole environment like a radiotherapy can do. So this has been created. There's trials in China and future projects. And so TAE Alpha Beam, that's the proprietary design of TAE Technologies. Sorry, TAE Technologies, but TAE Life Sciences, so the company. Where you can see, once again, we had a beam dump at the end, so same principle, the beam arrived at the end, you have to cool down this component. It was made with conventional manufacturing with a cylinder and grooves and sleeve and welds and flange and assemble and sealing joint. We decided to do one part with internal channel and all the interfaces we needed to put diagnostics on it. Plus, we decided to make it look cool. So it's a beautiful design. That's also something that additive manufacturing can do. You can have beautiful engineering, and it's still a functional part with a very high efficiency. And you can rely on materials that are existing, and in the future with the wish to develop better materials. And I will end with another sister company created also from the experience on the fusion. Because when you trigger the plasma and want to fire the beams, you have to store a lot of energy, much more than what the grid can deliver. So TAE has developed a proprietary technology to store energy and then deliver with specifically tuned algorithms the energy to the fusion platform. And so they found that there were a nice application as well with this power management unit, as you can see here, to create bays where you can connect that to, for example, solar panels and connect to then vehicles such as EVs, train, and do charging with this technology. And this helps to reduce the time charge and have also better efficiency overall. So these are as direct commercial application and will also contribute to the electrification, which is one of the challenges to face for the renewables. And on that, I would like to thank you and invite you to go to tae.com to have much more details, more than these 15 minutes, a bit more. I see this 0 on the clock, but to have more details about fusion, life sciences, and power solutions. Thank you very much.
Thank you, Vincent, for the sharing. Please remain on stage. I think the clicker has gone through a lot today. Please remain on stage. All right. I'd like to welcome on stage again our session speakers, Pauline and Professor Lee, and our keynote speaker of today, Michael, CTO, AM Technologies of Divergent 3D. Now, with Daniel as the moderator, we'll do one last deep dive today at how renewables impacts the environment. Ladies and gentlemen, another round of applause.
You have to be
on.
line. All right.
Maybe
Oh,
Yeah. I'll go at the end.
okay.
I can lean over.
All right.
Thank you very much for that. I really enjoyed a lot of those presentations. They were really interesting. Every single one of you shared a case study in which AM is used as enabling technology for sustainability. Can anyone share a common challenge that they see throughout the industry and how they dealt with it? Who'd like to take that one first? Pauline?
Yeah.
Well, thank you.
Okay. Yeah, through the global industry, because we have the chance to tackle many different industries and challenges. I think so far related to what goes with metal additive manufacturing, the confidence of the usage. So I'm glad to see that it has been used for different industries on stage already, but for the global impact for sustainability, it has to be, let's say, used by a wider and more impactful also industries. I mean, meaning in carbon usage and all of this. So I think one of the most challenging is the confidence we have on those technologies, the repeatability, uncertainty, and that will go with the, let's say, the standardization. So how I can assess my product through the standards.
It's interesting that you mentioned about confidence, because I thought in your talk this morning, Michael, you mentioned about taking that system approach and not just drilling down into small things. How did your company develop the confidence to just go, right, we're all in on additive?
So, you know, a lot of our team members come from different industries. So we had more than half of our team came from aerospace. Most of us had applied additive manufacturing in different contexts. So, you know, when tackling the problem of reinventing automobile architecture, we were sort of ready to apply everything. Really, it was quite liberating because we had the freedom to start from a true clean sheet versus, you know, a lot of our prior experiences were sort of, you know, iterating off an existing design, maybe doing a modification, but really being made free to apply it, I think really enabled us to implement something dramatically different from the way any automobile has been manufactured before.
And at the other end of the scale, Professor Lee, your application is really small for additive manufacturing. You said to me beforehand that you don't consider yourself an additive manufacturing expert. How did you A, come about additive manufacturing for your project, and B, how did you approach EOS as your partner in that?
Sure.
Or have we got
Oh, do I need to use a
I
mic?
think
Oh.
no, you're right.
Oh, okay, sure. Okay, thanks. So I've been tracking the progress of additive manufacturing for a while. I think in the past it's known as like rapid prototyping, 3D printing, then obviously now the inward is actually additive manufacturing. So I think over the years, we have been, as mentioned, been tracking the progress. In the past, I think the main concern is actually it can't achieve the kind of feature size that we needed, right? So we are actually looking at tens to hundreds of micron, right? So when I first started looking at AM, I think that time, I think probably you can only do maybe close to a millimeter. But I think the last couple of years, the technology have actually advanced quite a bit. I think in particular, doing copper, because for thermal measurement application, we need high thermal conductivity. And for a lot of the AM machines, the laser power then becomes an issue, right? For example, with the machine that we're currently using is having a 1 kilowatt laser. So that actually allows us to actually have better control in terms of the minimum feature size. Yeah. Then working closely, how we sort of end up working with EOS, I think that because I know somebody at EOS. So he actually started off also focusing on thermal management, right? Then I think he then took up a position with EOS. So I think it's kind of coincidental in certain sense, but certainly I think through NAMIC that also facilitated some of the so-called process, right? Because NAMIC actually been very helpful in sort of identifying what are some of the possible technologies that can help us realize the kind of feature size as well as the unibody, the design. Yeah. So it's actually through both person contact as obviously through NAMICs as well.
Thanks very much. And Vincent, the machinery that your organization is creating is incredibly complex. How did you start your journey of identifying what parts you thought should be 3D printed?
So really, the one that has the most solicitations, as I said, you have a very, very hot plasma in the middle. So, and there's a long experience in fusion. It's not a new technology. It has been developed since the 50s, but with the tokamak. And so we know that these parts are prone to failure because they receive high heat loads and some stresses as well from the magnetic forces from the plasma when the plasma moves. So how do you avoid having a joint to fail and to leak inside the vacuum chamber? Well, remove the weld, right? So have a complete unibody part. And that makes a lot of sense for us to move to this technology. And then when we talk about the back end, as I explained, you have to transform this thermal and radiation energy to vapor, basically, and then turbine and alternator to create the electricity to the grid. So usually how it's done is piping, that's done to molded turbines and everything. Well, if you're able to optimize everything, reduce your pressure drops, have organic design, smooth transitions, minimum number of parts, which mean minimum risk of failure, more reliable systems, and easier to maintain as well. You have to think that there will be humans working on this machine to assemble and then to maintain. When you see how complex it is to enter on a nuclear facility, you have to reduce the number of parts. And so this makes sense on these very high heat flux components. And then it's when we are faced to the reality of the market. As I said, some of the components are not that exciting on the design, right? It's just a block with a channel inside. But the part works for half of the price, and we have it in 1 month instead of 3. So for a private company like TAE, we delivers on milestones. And in the future, I really hope that we'll have to build a lot of fusion power plant on the planet to answer the energy needs. It will be a massive production of parts that we'll have to do. And additive manufacturing is the right answer to that. Just to finish, it doesn't make sense to replace everything with additive manufacturing. Only the parts that are really answer to that, like a pipe, you don't need to print a pipe. The industry is good enough on that. Or a vacuum vessel, you can do that from a plate, no need to print. But they are like key elements where you can save money, increase reliability, and improve the performance, the overall performance.
I'm going to, before I move on to my next question, I would like to open any questions to the floor. If anybody does have a question, please raise your hand. A microphone will be passed to you. If not, I can continue with my question. I'll give you 5 seconds. No, okay. My second question is a little bit more complex. During a talk I saw at TCT 360 in the UK, Dr. Phil Reeves had some analysis about grid efficiencies. And we hear a lot of talk about how one of the benefits for additive manufacturing is this decentralization. But Phil Reeves' assessment was that in some cases it might be better to manufacture a part under a wind farm in Norway and ship to a country that uses fossil fuel. It might be more sustainable for our planet there than to manufacture in situ. How And I'm going to pass this to you, Michael, because I noticed in your talk you had a lot about where your plants you'd like to be in the future. How are you tackling energy efficiencies at Divergent?
Yeah, no, it was a great point by Mr. Reeves. We are taking into account where we place our facilities very much the local energy mix and looking at countries, the countries that have renewables and are on the right trajectory are going to have the advantage in terms of attracting future facilities. So when we look at, for example, the energy mix across the EU, there's some really interesting countries like Slovenia, which has really high amount of nuclear content already on their energy grid. They've made the right kinds of investments to attract, I think, additive investment and future digital manufacturing sites. So just one example, there's lots of great options in Europe, really, but then there's a lot of pretty bad options as well. So you do have to take that into account in our future facility planning, as all of our customers, when we look at least on the automotive segment, are driving, zero emissions requirements, 2035, targets that are extremely aggressive and are going to require a very different approach to, come anywhere close to us meeting those.
And for you, Pauline, how does SETIM see energy efficiencies in terms of where it manufactures parts?
That's a hard question to answer, especially when you're talking to a SME that will need to prove the carbon efficiency of the product they will sell to plane manufacturers, for example. Yeah, I think that we just started to prove that additive manufacturing is working, and thank you for the different testimonies today and across the week. Yeah, this is something that we need more data.
Yeah.
So we need definitely to start building this database, and thanks to now, intelligence artificial, that we can get a better projection of how would cost in carbon footprint the next generation of parts. Not all the parts. So some parts will still be manufactured at conventional, though we know their carbon footprint today, but for additive manufacturing, then we'll need to have more data to address this specificity about net zero for the 2050, which is most of the challenges that the industry will need to address later on. Mainly for SMEs that will need to integrate these new technologies inside their facilities and manufacturing production.
It's interesting you mentioned about getting a bigger data set as well, because one thing that struck me during your talk was about the application with CNES and the huge data set that they created for you.
Sorry, we created
you created
the data
for them, sorry. How do you think that could help people in the future collaborate and get to a point where they can use your data to enable themselves to make additive manufacturing if you were an SME? Can you get your hands on that data?
We do.
Yeah.
We give access to the French SME.
Yeah, okay.
They have the access, yes. For I mean, not the direct access of it, because some data are mainly, the recipe for manufacturing those parts are confidential. They belong to the one that developed them. But meaning that the manufacturers goes with EOS, we worked with all the different manufacturers and all the different part providers in France. And yeah, we give access in a sort of way, the analysis. So if I want to reach this type of mechanical properties, then you need to be in that range of laser speed, or that range of the thickness of the layer and things like this. So this will give access to the French SMEs.
And going back to the grid efficiencies, Professor Lee, your application is basically about how we save energy on the grid. How do your company see grid efficiencies in general across the globe? And is there anywhere specifically that you're tasked with attacking?
Okay. I think using Singapore as an example, right? So for Singapore, we don't really have energy resources, right? Probably with the exception of the limited rooftop space for solar. Otherwise, it's mainly through the energy imports, right? But if you look at the government strategies, right? So one of the latest one is actually on regional power grid, right? So specifically, we're actually looking at importing clean electricity from across the region. In fact, I think we are still keeping the Australia options open, right? If they can actually address the financial issues. Yeah, so I think one way is certainly if we were to import the clean electricity, then you can use it for more energy intensive industry, including possibly manufacturing. The other is actually more of a collaborative approach, right? So meaning that you need not necessarily have the manufacturing base in Singapore, but you can actually set up in the region, for example, in Indonesia, in Malaysia, which have an abundance of renewable energy sources. Yeah, so I think really it needs to be more of a collaborative and rather just say, well, it has to happen within the national boundary. Yeah.
It'd be interesting if we could take TEA's eventual product and give it to all of the places that use fossil fuels at the moment. Is that on the roadmap for TEA? Do they see the future in renewable energies in growing manufacturing economies, let's say, and using that technology to power those growing manufacturing technologies?
Yes, completely. And it won't replace all the renewables. It's actually a complement. It's great to have solar panels on the top of a roof of a building, windmills eolian energy when you have enough wind, obviously. But think about also how do you want to include a large-scale energy provider to your grid, either it's efficient or not. But first, the source of the energy, when you have a country that is very small or highly with a dense population. I take example in the United States, it's a huge country, they have huge desert. You go to Arizona, you have solar farms. They have the place to put thousands of solar panels or huge installations. It's okay, there's just a city there and then it's wildlife. But when you are in small countries, me coming from France, we relied on 75% of nuclear energy, if I'm not wrong. We know there's a risk on that, is fission nuclear in this case. It's a very clean compared to burning coal, obviously, but it's a very complex installation, very costly to construct, to maintain, and to decommission. We never talk about that. The politics never talk about that, but it's a very important thing to consider. And think about fusion power plant. So it's safe. There's no meltdown with fusion. When the plasma has a problem, it just shuts down. There's no meltdown. There's no explosion like fission. It's much more complex in terms of physics, obviously. That's why we are still in R&D phase all over the planet on different techniques. But we could have a fusion power plant close to an urban population, which means you don't need a long infrastructure to transmit your energy to where you need this energy. So you minimize your losses, right? And you can have also a more political acceptance, I would say, from the population, right? That are not always consulted. I can tell right now in France we are building 5 big nuclear reactors and the population is not happy about that. Our needs will be covered, but we know there is a risk behind that. When you see in other countries where they are now building new coal power plants, what's the price to pay on the environment? Today we know that it's a high price tag, and it's not only the country, it's the whole planet, so the whole humanity. So that's a choice that we want to make for the future. And I really think we won't get rid of the fossil fuels, that fast, because, well, first we'll need them just to build renewables, right? And it will take a long time to transition to renewable, but we have to be smart, and I think that is based really on political decision and investment and a worldwide coordination, as you were saying, not only on how do we need the energy, but how will we manufacture that. And that's where additive manufacturing, by using the minimum amount of material and having everything optimized, there are all the bright minds on the planet in every country to have engineers and physicists and technicians working on that to build much more efficient installations.
You mentioned some government policies there, and a lot of the governments on the globe are currently focused on creating an electric vehicle bank that is better for the environment, particularly in the UK, even if our government did just announce that they're going to push it back by 5 years. But when I look at electric cars, currently a lot of them are just the same design as a combustion engine vehicle. And I'm looking at you here, Michael, as the man in automotive, is the key to unlocking better electric cars coming in design?
Yeah, I think that's an important observation. You know, a lot of times when we're deploying a new technology, there's sort of a kind of a sequence that happens, right? You know, they tend to, the crawl, walk, run analogy, right? So they started with what they knew, right? You take an existing powertrain and you rip it out and replace it with an EV powertrain. It's basically the same car with the same, largely the same sorts of safety requirements, and you know you're at least going to check those boxes, right? But, you know, in undertaking that, I mean, there's been just a tremendous amount of capital around solving that problem statement and not really progressing to the future state that we really want to get to. Actually, that was the inspiration for Divergent Technologies. If you look back at Kevin Zinger's background when he founded Coda Automotive, it was actually a predecessor or, you know, of Tesla, and he actually created a battery factory in China, first lithium iron phosphate prismatic battery cell, brought it to the market, did a conversion of a conventional auto to an EV, the first one that was done, I don't remember the exact timing, but like, let's say early 2000s, and ended up spending an enormous amount more money on that project than the entire battery development, right, to put it in perspective. So when you think about sort of some of the, I don't know, it's almost hard to describe with any other word, but perverse sort of approach to deploying new technologies at times, we really got to get a lot smarter about using tools like additive manufacturing to more quickly make the transition to that run state so that we are not spending so much time and destroying so much capital progressing from those earlier phases to the final target where we really need to arrive at much sooner, I think, to really stem you know, a lot of these kind of parasitic losses across you know, that whole development chain.
And Pauline, you talked about earlier on in the conversation about confidence, and a video that Michael showed this morning of the crash test for the bumper, the additive manufactured bumper, kind of like is the way to do it. And obviously he said he was very focused on the quality of parts and how they work. How do you go about building up confidence in companies in additive manufacturing?
I think you have to prove the performances. So we tend to give them the keys, first of all, to understand, look for the right parts. Not all of their parts will be manufactured. So you look at the right parts, and today we can find on the market some solutions to help in sorting out the catalog of the parts, global parts, to help in identifying which one is the right one or which kind of families of parts are the right one to look at. And then we help them in looking at the right way of thinking the design. Could be the part itself, could be around the system. You know, sometimes you just, we were mentioning about the process of assembly, that when you get only one part, then you don't need to assemble it, but it's a global system. With some additive manufacturing process, you can also have mechanism printed, meaning parts that have movement between each other. They are printed at the same moment. So it's something brand new. You cannot achieve with LPBF because it's fusion, but when you use indirect processes, you can have those kind of mechanism as well. So you have different parts at the same time, so saving issues, and you don't have any problem of assembly. So we help the companies to identify what is the right process, what are their benefits. We build with them the return on investment plan. And time to time, we'll help them because governments are also helping in providing funds. We help them in fulfilling those requirements and build their facilities, investment, to make the right choice. So we help them in unrisking the investment on metal AM. So it's the global aspect. It's not only about technical, it's also about how I can integrate those new technologies inside my manufacturing workshop. So it goes with the technical, and then it goes also with how we can train their teams. Because you cannot hire at the same time as you actually acquire a new machine. So yeah, we will help them in train their teams and get the right skills for the right stage of their manufacturing. And we also build what we call shared platforms. So we take the risk. We acquire machine on the shelf. We have a lot of from different manufacturers. And then we will build a R&D program to help them grow their knowledge. They come to our platforms, they use them. Sometimes they qualify their parts, and sometimes they buy secondhand the machine we bought 2 years later. So they integrate, they know already how it works, they already certify their part, the recipe to print it. So either it's a B2B one-to-one help and support, either it's through a shared platform. So they share only the time of it. So really we take the risk, and they benefit from this experience as well.
We talk a lot about the benefits of AM in its help towards the quest towards sustainability, but there is also an element for, particularly from the OEMs, about how sustainable the technology may be. We aren't sure whether it's greenwashing or whether it's marketing. What's the challenges that you see? And I'll open this back up to the floor. What are the challenges that you see that additive manufacturing has towards sustainability in terms of things like material usage or power usage or anything like that? Does anyone have a strong opinion on that? No.
Yeah, I have.
Okay.
First of all, the material itself, you need a lot of energy to get the right powder, the right form, the right shape of the powder to be used when we talk about powder. So this is the first, the availability of those materials and the energy consumption. And then there will be also the price of the investment. When I'm talking about metal, I'm not talking about plastic. So yeah, the investment. So this is why it's not yet, let's say, available for a small company, depending on their capabilities of putting the right product on the right market. So yeah, this is a challenge also that needs to be tackled for the next years, in how we can scale up the use of the additive manufacturing, metallic, to make sure that we get the price efficiency and energy efficiency also on the different raw materials and printers.
And Professor Lee and Vincent, do you see when you assessed the parts that you made, how did you find the return on investment and the justification of the price of the materials, and how did that go down in your companies, organizations?
Okay, so if you were to do a part-to-part comparison, sometimes or maybe oftentimes additive manufacturing will be more expensive, but if you were to look at the entire system comparison, right, the fact that you do away, for example, the joining process, if you were to make use of the unibody design. So if you do a whole system comparison, additive manufacturing, in fact, can be very competitive, right? So we've been doing the cost simulation with our partners, and if you're focusing, for example, as mentioned, the unibody, the cold plate design that we're looking, so in fact, it's actually within like 20%. But then obviously it has this additional advantage of being leak-free. So that being the case, then the overall maintenance cost will be actually lower compared to conventional design. So if it really take a total cost of ownership perspective, then I think AM can be, in fact, very attractive.
Yeah, for fusion technology, it's a little bit different because, as I said, we are still in R&D phase. So we build one machine, one R&D platform for now. So what we are looking is so far we started from scratch 2 years ago. So looking what's available in the industry. So that's why I mentioned the Gyrocop 42 that's been developed for aerospace with a long research from NASA. And we can use that because the requirements we have are very close to a rocket nozzle, although we are even more demanding than a rocket nozzle because we operate in ultra-high vacuum. And so the difficulty now is how do we go further? Because the industry doesn't exist for this application. It's not automotive. We are not looking to print millions of parts like in automotive. And so that will work with partnerships with industrials. We have worked with EOS more on the training and how to do additive manufacturing. But we have discussions also with national labs, universities, and private companies that do research in materials. Like refractories, other alloys, and how do you mix different materials as well, because sometimes you need a shield and then a heat sink behind, so how do you do the transition on that? That's something that will be likely developed in fusion, and TIE is one of the pioneers developing that. We're not the only one using additive manufacturing, but the few. So far it's all usually made with very thick plates that you bond together and then you mash that down. When you go to very specific alloys, you don't have the semi-product available, or it's available in 6 months. So how do you comply with that? Well, you build that from additive manufacturing. That's a solution as well. But you need the supply chain to be here, and that's something you have to build. And so for fusion, obviously, it's based on trust because it's not actual industry, not yet. But I'm really confident that all the development that will be done here will be used for somewhere else, like in aerospace, medicine. We also already see with the life sciences that just experience on beams to fire a plasma, we can treat cancer. So that's what's beautiful also with physics and engineering is that, and it's an advice also to the additive manufacturing companies or research lab. Do not restrain yourself of asking around and communicating with companies that are not in the mainstream consumer products or that build crazy stuff as we do, or new 3D printed buildings, because there's room for innovation. I think the engineering and science has few limits on that. And there's a strong commercial potential as well. So there's a potential market to develop on that. Yeah, these are the challenges and solutions we can find.
And Michael, you were nodding your head there. Does your application and your company show that if you kind of go all in on additive, say this is the method that we're going to use, that you can almost achieve anything with it?
I mean, our process is fundamentally agnostic to any particular AM technology, and you know, we're not going to print, as I think some examples were given, print a tube necessarily. Sometimes we might. It might actually make sense. Depends on the tube. But you know, there's a lot of cases for using commercial off-the-shelf materials and integrating them using additive as a solution to more easily integrate lower cost solutions into a complex structure. I think one of the sort of central needs I see around AM technology is a lot of how it started. You know, I'll talk about laser powder bed fusion primarily, since I think that's what many of us are focused on right now. Is, you know, we put these initial requirements in place. They really came from a very aerospace-driven perspective, quality perspective, and that may not necessarily be what's required. And so we see these types of requirements flowing into the standards and represented in the standards. And a lot of what, you know, the challenge when I joined Divergent, and you know, part of what attracted me to it was, you know, quite literally taking that whole stack of assumptions and then questioning each and every one of them about, you know, is that really necessary? Why did we pick that PSD for powder? Why did we have to be that morphology? Why can't I use a wider PSD and make this more economical? Oh, by the way, making it more economical actually makes it more sustainable because I'm using more of the output of the atomizer. What are the benefits of this? You know, let's not assume it's making it worse. It's actually, there's benefits. And as we're scaling productivity and driving to higher powers, using these wider and broader PSDs is actually better for the process. So, you know, these kinds of assumptions that we're sort of naturally making about the technology, I think is in a lot of ways kind of holding us back from where we really need to progress it to. And so I think that's a bit of a challenge for, I think, some of the really talented individuals here in this AM ecosystem in Singapore to really engage with those same list of assumptions that I think a lot of us are making about the technology and what they can actually do. You know, how many times have I seen that chart for, you know, this is the print rate of laser powder bed fusion, and here's DED, it's faster and lower cost over here, and this really bigger wire, you know, DED process is even better. You know, we're printing laser powder bed fusion right now today at rates higher than where they show the, you know, some of the powder DED type processes starting. So I don't, you know, I think anytime you see a chart like that, you should really challenge it and find a way to break it.
That's a really, really good point to end on. Thank you very much to all of our panel. I've really enjoyed it. Thanks a lot. Thank you.
And thank you so much. Can I please invite the panelists and the moderator for a photo, please? All right, another round of applause for our panelists and moderator. And with that, we have come to the end of the 12th edition of the Global AM Summit. Ladies and gentlemen, can we give another round of applause for our panelists and speakers? Now, throughout this summit, we have explored how AM technology has disrupted the traditional archetype of manufacturing with the remarkable potential to drive various industries towards greater self-reliance and sustainability, at the same time spark creativity and propel innovation. Now, through the partnerships and initiations today, we have also expanded capabilities and catalyzed a transformative shift of both processes and mindsets, breaking down barriers to the adoption of AM technologies for a more sustainable future. Now, on behalf of the National Additive Manufacturing Innovation Cluster, I'd like to extend our most sincere thanks to all of you in making the 12th edition of the Global AM Summit a success. As NAMIC continues in its efforts to support and accelerate the adoption of AM in the manufacturing, supply chain, and R&D sectors, we hope that this summit has also provoked you to consider this in your own workplace and industry. With that, once again, my name is Lorene. Thank you and see you next year.